Every single time you stream a movie or hop on a video call, you are tapping into this incredible technology that's it's pretty much invisible to us. So today, we're going to pull back the curtain on the lasers and fiber optics that are the true backbone of our entire digital world.
I mean, think about it. It really does sound like magic, right? The idea that all the data, all the trillions of gigabytes zipping around the planet every single second are actually being carried by beams of light. So how on earth is that even possible? That's the big question we're going to tackle right now. All right, so if you want to send information using light, you can't just, use a regular old light bulb. Nope. You need something special. You need a really pure, super controlled kind of light. You need a laser. So first things first, we've got to figure out how you forge that perfect beam.
This right here, this slide gets right to the heart of the difference between, say, a lamp in your living room and a laser. An ordinary light bulb works by what's called spontaneous emission. You pump atoms full of energy, and they just release that energy as photons of light whenever they want in totally random directions. It's chaotic, just like a crowd clapping all out of sync. But a laser? It relies on stimulated emission, and that is like a perfectly coordinated slow clap, where one clap triggers the next, creating this powerful, unified wave.
Right, so the key idea here is this concept of cloning. With stimulated emission, you take a single photon and you use it to knock another photon out of an atom that's already excited. But here's the amazing part. The new photon that pops out is a perfect copy of the first one. I mean, same direction, same frequency, same phase, they're identical twins. This is the absolute secret sauce for creating a powerful, focused beam of light.
So knowing what stimulated emission is, that's one thing. But how do we actually build a working laser with it? Well, it really boils down to three key secrets, or you could call them ingredients, that we need to get just right.
And the very first secret is creating this really weird, totally unnatural situation called population inversion. See, normally atoms are kind of lazy. They prefer to just hang out in a low energy or ground state. To make a laser, we have to pump so much energy into a material that we completely flip that upside down. We get more atoms in that high-energy, excited state, all just waiting on the edge, ready to release their photons. It's kind of like setting up a massive field of dominoes, just waiting for that first push.
And here is the whole recipe, laid out perfectly. First, you have pumping. That's just us adding the energy, maybe from a flash of light or an electrical current. That leads to step 2, getting that population inversion we just talked about. And finally, a single photon kicks off a chain reaction of stimulated emission, creating that incredible cascade of cloned photons. So where does this chain reaction actually happen? Well, that brings us to secret number 2, the resonant cavity. The best way to think about this is like an echo chamber, but for light. It's basically just 2 mirrors, placed at either end of our laser material. The photons bounce back and forth between these mirrors over and over, passing through those excited atoms again and again, and every single pass stimulates the release of even more identical photons. The light just gets amplified like crazy.
And the third secret? Well, that's the material itself, what we call the gain medium. The type of atoms you use actually determines the specific color or wavelength of the laser light. So for example, the very first laser ever built used a synthetic ruby crystal to get that deep red beam. The lasers you see in barcode scanners, they often use a helium neon gas mixture for their red light. And really powerful industrial lasers might use a special crystal to create an invisible, high-energy beam. The material really does define the laser's personality.
Okay, so we've forged our perfect beam of light. We've got our laser, but now we need a way to guide it, a way to send it across a room or even across an ocean. And that brings us to the second massive piece of this puzzle, the optical fiber.
The magic behind fiber optics is this beautiful, elegant physics principle called total internal reflection. Now, it sounds really complicated, but the idea is actually super simple. If light is traveling through something dense, like glass, and it hits the edge of something less dense, like air, at just the right shallow angle, it doesn't escape. It reflects perfectly, as if it just hit a flawless mirror. Absolutely no light gets lost.
And believe it or not, there is a magic number for this whole effect. For light going from a typical piece of glass into the air, that angle is about 42 degrees. We call it the critical angle. So as long as the light beam strikes the inside surface of the glass at an angle that's greater than 42 degrees, it is trapped. It will just bounce and reflect down the glass forever, completely unable to escape.
And a fiber optic cable is engineered specifically to make this happen. At its very center, you have the core.
this incredibly pure strand of glass where the light travels. Wrapped around that is the cladding, which is a layer of a different kind of glass, precisely designed to create that perfect reflective boundary. But you can't just shoot light into it any old way. The angle of acceptance defines a specific cone at the entrance, and only light that enters within this cone will be successfully trapped and guided down the fiber. The size of that cone is measured by the numerical aperture. A bigger aperture means the fiber is better at gathering light, but it all has to work together to create what is essentially a perfect pipe for light.
So let's recap. We have the perfect light source, the laser, and we have the perfect pipeline for that light, the fiber optic cable. So now, let's put them together and see how they form what is essentially the nervous system of our entire modern world. This is the whole system, right here, in a nutshell. You have a laser acting as the transmitter. It turns digital ones and zeros into flashes of light. Think of it as light on is a 1, light off is a 0. Then, the optical fiber is the highway, guiding those light pulses perfectly, even over thousands of miles. And at the other end, you have a detector, which sees those flashes of light and turns them back into the ones and zeros that a computer can understand.
So let's trace the journey of a single piece of data, your voice on a call, maybe a single pixel in a movie. First, it's encoded into billions of laser flashes every second. Then those pulses are fired into the fiber. Total internal reflection takes over, keeping them bouncing perfectly along the path, even when the cable bends. And finally, at the destination, a sensor decodes those light pulses back into the original information. It is so elegant, so simple, and it all happens at pretty much the speed of light.
And that's what's so incredible about all of this. This isn't just some amazing feat of engineering, it's a triumph for understanding fundamental physics. By figuring out how atoms release photons and how light behaves when it hits a boundary, we have actually managed to wrap our entire planet in a web of glass that connects all of us. From cloning a single photon to trapping it inside a tiny strand of glass, we have well and truly tamed light. Our global society is literally built on top of this mastery. So, as we look to the future, the real question isn't just what we'll master next, but what we'll do with that mastery. What new worlds could we possibly build if we learn how to manipulate not just light, but maybe gravity, or even the fabric of space-time itself?